Hello all, welcome back to this video on two greedy algorithms for MST, that is minimum spanning tree. First algorithm is Kruskal's algorithm and the second algorithm is the Prim's algorithm. Both these are greedy algorithms, work well because they make really the best local choices at each step. Why these algorithms works best? Because they make locally best choice at each step. That is the main functionality of the greedy algorithm. So these local choices guarantee a global optimal output also. As we are making the local best choice, they end up in making global optimal result. Okay. So diving into deeper about minimum spanning trees. First, we will go through the Kruskal's algorithm. What is the Kruskal algorithm and how it works and what is the time complexity? Before going into what is Kruskal's algorithm, we'll look into what is exactly a spanning tree. Okay. Imagine you have a network of cities connected by roads. A spanning tree is a way to connect all the cities with fewest possible roads. Connecting all the cities with fewest possible roads. Okay. This is the concept of spanning tree. While making sure there are no circles. What is the constraint? No circles should be made. So that everything stays connected. Everything should stay connected. This is the concept of spanning tree. Imagine you are connecting all the cities with fewest possible roads, covering everything with no circles formed. Okay. What is meant by circle? A path in a graph that starts and ends with a same vertex. Circle is nothing but a path in graph where the start and end point is the same vertex. Okay, that is called circle. Without circles you need to create spanning trees. So now we want to do this efficiently, that is creating spanning trees efficiently and cheaply, which brings us the concept of minimum spanning tree. So spanning tree, doing it efficiently and in a cheaper way. Is nothing but minimum spanning tree, MST. So on a whole, what is the definition of minimum spanning tree? Is a subset of edges that connects all vertices with the minimum total edge weight. So what is MST? First point, subset of edges. Second point, connects all vertices. Third point, connecting all vertices with minimum total edge weight. Minimum total edge weight. Okay, the edge weight should be minimum. So this is how the two algorithms work on the whole, that is Kruskal's and Prim's work on this concept of MST. Subset of edges connect all vertices with minimum total edge weight. This was the overview of spanning tree and what is minimum spanning tree and what are the steps followed to create minimum spanning tree and what are the different algorithms. We have just had an overview. We will dive into deeper regarding the two algorithms now. Diving into deeper, first Kruskal's algorithm work by picking smallest possible edge. Okay, picking smallest possible edge at each step. What does this remind of? Taking optimal decision locally. Okay, as long as it does not form a circle. What was our constraint? It should not form a circle. So, on a brief, what are the steps involved in Kruskal's algorithm? First, we will sort all the edges by weight, that is ascending order in the increasing order of the weight, because we need to pick the minimum amount of weight, minimum amount of edge weight. So, second step is then we'll go through disjoint set unit to detect cycles. If there are any cycles formed here or not, we are checking using disjoint set union. Okay. We are taking the help of disjoint set units because we will keep track of nodes. We will keep track of nodes that are connected without forming any cycles. Okay. We are using disjoint sets because we will keep track of nodes that are formed without that are connected without forming any cycles. So in the first step, we are sorting all the edges with an ascending order. We will select the edge with minimum weight. And second is we are using disjoint set union to detect any nodes that are connected or that are forming any cycles. If it is forming cycle, we will skip that, and if it is connecting to the nodes, we will catch it. Okay. Start with an empty MST, minimum spanning tree. We will start with empty MST. For each edge, that is U and V, we will check if U and V are in different sets, not already connected. We first check that U and V are not already connected and they are from the different sets. Then we will add it and form a set. Then we will add it to MST. Okay. I hope you are getting First, we'll sort all the edges in the ascending order, pick the smallest weight edge, and we'll check whether it is connected or whether it is forming a cycle. Then we'll start with empty MST, that is minimum spanning tree. For each U and B, each U and B, that is node and edge, whether it is not in the same set, that is if it is in different set, then we will add it to MST. Add that edge to MST. If it is already not connected, then we will add it to MST. Union sets of U and B. Okay, then we'll form the union sets of U and B. This will update the disjoint set union, that is DSU, which shows that these two nodes are now connected. Okay, we will keep track of these two nodes and update DSU, so that saying that these are already connected. So when the MST has reaches to n-1 edges, then we will stop the algorithm. Okay. So when once our MST has n-1 edges, n is nodes, and we have n-1, 1 less than the number of nodes, that is edges. When we have n-1 edges, we will stop the algorithm that we have connected all the edges. Nothing but the concept is simple, that we will majorly sort the edges in an increasing order of weight. We'll pick the minimum weight from the edges and we'll start with a node. We'll check whether it is forming a cycle or not. If it is not, if the node is not forming a cycle, we'll go to the edge and we will add it. If it is from the different set, that is, we are confirming that it is not already connecting any vertices, then we will add it and update the disjoint set, and we will update the disjoint set union, that particular edge and particular edge is already connected. We'll go for another edge. Okay, we'll go for another edge. Once the MST, we'll add each edge to MST with the minimum. First initially it was empty. Keep on adding the edge to the MST. Once the MST reaches to n-1 edges, we will stop the algorithm. This is very simple and clear. So what is the time complexity? Because it is involving sorting and union, that is disjoint set union operation. O of E log E is the time complexity. Okay. This works very efficiently for the sparse graphs. Kroskal algorithm works very efficiently for the sparse graphs. So what is the overall goal of Kroskal's algorithm? Overall goal of the Kroskal algorithm is forming spanning tree, that is connecting all nodes. We need to connect all the nodes, as we have said, connect all the cities, connect all the nodes with minimum number of edges. Okay, minimum number of edges without forming cycles. That is why we are first initially sorting all the edges, and whether checking it is forming a cycle or not. No cycle should be formed. Then we will keep on adding to the MST, joining all the nodes. Okay. Once we have reached to n-1, 1 less than the number of nodes, that is edges, will stop the algorithm. That is the main goal of the Kroskal algorithm. And the total edge weight should be as small as possible. One more constraint is total edge weight, edges weight should be as small as possible. Okay, this is the goal of Kruskal algorithm. Now coming to the second algorithm, that is Prim's algorithm. So first we will look into what is the goal of the Prim's algorithm. To build a minimum spanning tree, build a minimum spanning tree, a set of edges that connects all vertices with minimum total weight, no cycles here also. Okay, build MST with a set of edges that connects all vertices with minimum total weight, no cycles. This is the goal of Prim's algorithm. Start from any vertex and grow the MST. This is what is going on very common. Start with any vertex and we will initially set MST to 0, and then we'll grow the MST by adding the smallest edge or edge with minimum weight that connects a new vertex to the current tree. So we'll start with a new vertex, grow the MST by adding a small edge that connects to a new vertex to the current tree. This will add a new vertex to the current tree. Okay. So what are we doing here? What we were doing earlier in Kruskal algorithm, we use a disjoint set union, that is DSU. But now we are taking a help of minimum heap, that is a priority key for edge weights, to track whether they are already connected or not, and also to track whether they are connected or edges are already connected or not, already used or not, and also to check whether no cycles are formed. Okay, whether cycles are formed or not. Diving into deeper, we'll always pick smallest weight edge. Okay, so initialize a priority queue. Priority queue is nothing but like a to-do list. It is also nothing but like a to-do list where the cheapest edge is always on the top. It's nothing but a to-do list. Priority queue is nothing but a to-do list where the cheapest edge is always on the top. We will use this as always pick the smallest weight edge. Okay, we will always pick smallest edge weight. Okay, first we'll pick a vertex, we'll mark it as a visited list. We'll pick a vertex and we'll mark it as a visited list. Push all its connected edges into the heap. We'll push all the connected edges into the minimum heap list. Okay, then we'll pick the minimum weight edge if the edge is connected to a new vertex. We will pick a minimum edge weight from the queue. This is our to-do list. Nothing but minimum heap, or you can call it priority queue. We will start with a vertex, we will mark it as visited, first visited, and then we will pick minimum weight edge from the queue that connects to an unvisited or the new vertex now. Okay, this is our new vertex. We will add the edge to the MST. First, our MST will be set to 0. We will set the MST to 0, and now we will add this edge to MST and new vertex to the queue, and we'll also add this new vertex into the priority queue. Okay, we will push all outgoing edges from the new vertex also into the queue. We will push all the outgoing edges from the new vertex also into the queue, so that it will keep the track of the edges. Okay, repeat until all the vertices are visited. For example, if there are 4 vertices, we will repeat this step till all the 4 vertices are completely visited. What is the time complexity? Time complexity is O big O of E log V, because we are using minimum heap and adjacency list also. E is the number of edges and V is the vertices here. E is edges, V is vertices. So, comparison between Kruskal's and Prim's algorithm. What is the strategy of the Kruskal algorithm? This is edge based. We have seen that this is edge based. And what is Prim's algorithm? This is vertex based. We are tracking the vertices. First we are taking the new vertex, and also we name it as visited, and then we'll again add a new vertex. Okay, this is vertex based. And what is the data structure? Here we are using disjoint set union field. We are maintaining a minimum heap or priority queue to store the vertices. What is Kruskal algorithm best for? Already we have said that this is best for sparse graphs, and Prim's algorithm is best for dense graphs. Okay. What is the time complexity? Time complexity is big O of E log E. E represents edges. In Prim's algorithm, the time complexity is big O of E log V. V represents vertices. What are the applications? Okay. In designing network layouts like internet cables, water lines, internet cables, water lines, and power grids. Okay. In network design, computer networks in like LAN and WAN routing, designing and routing, clustering in machine learning and image processing, and even approximating solutions for tough problems like traveling sales persons. Okay, designing algorithm for traveling sales persons. Okay, these are the applications of minimum spanning tree. Thank you.